Good afternoon, everyone. I hope you had a good lunch. We are going to be starting the next session, which is on climate change and carbon. So our first speaker for today is Lisa Matthews. She is joining us online. She's a PhD student from the Netherlands with the Environmental Policy Group and Soil Chemistry Group at Wageningen in University in the Netherlands. Yeah, so.
Hi everyone, I'm Lisa Matthews and I'm a student based at Wageningen University. My PhD looks at carbon accounting, or how carbon sequestration is estimated when it isn't measured or sampled directly. Now, I'll be talking about how carbon in grasslands is reported in the climate policy space. So instead of starting with a specific grassland, talking about its carbon dynamics and then linking that up to climate change mitigation, I'll be doing this other way around. I'll start with climate change, then move on to reporting carbon in grasslands, and finally to the South African context. These are two figures from the IPCC's assessment report. This is an important and policy-relevant report which synthesizes the science around climate change. And in these figures are different scenarios modeled by different colors. And in the figure on the left, you have scenarios which show cumulative carbon dioxide emissions on the x-axis and global warming level on the y-axis. And then on the right, you have the same scenarios, so the colors match up, but now you have on the y-axis carbon dioxide emissions emitted annually. So this is on an annual basis, and then by year. And what I would like to highlight here is this threshold of 2 degrees. So the Paris Climate Agreement aims to keep warming below this level, so it's quite an important threshold. But the only scenarios that are meeting this, if we look at them over here, the interesting thing is that they all dip below 0. And what this means is that at some stage, what they are saying is that to meet the Paris Climate Agreement, we need to switch from emitting carbon dioxide and actually absorb more than what we are emitting. Now, the tricky part about this is that we haven't made nearly enough progress in tackling climate change. Annual emissions haven't significantly decreased yet. Climate change is an accumulating problem, so you aren't only dealing with emissions from the last year, but all emissions going back to the Industrial Revolution. Those greenhouse gas emissions are still sitting in the atmosphere and still contributing towards warming. This puts us in a very challenging position if we hope to be removing more carbon than what we are emitting. And this also puts a lot of pressure on ways to try and sequester carbon. And this is why natural ecosystems such as grasslands are getting far more attention now, because they have this ability to sequester and hold on to carbon. So how do grasslands feature in South Africa's climate plans? So South Africa is a party to the United Nations Framework Convention on Climate Change, also known as the UNFCCC. And they aim to coordinate a global response to climate change, and they meet together at the climate COPs. As a party to this convention, South Africa reports on the greenhouse gas emissions, they report on mitigation activities, as well as climate change impacts, adaptation measures. And this is all done in their biannual transparency report. So along with reporting on energy production emissions or industrial processing, South Africa also reports on all carbon changes in their grasslands on a national scale. When reporting carbon sequestration in grasslands, a very specific calculation methodology needs to be used. This is so that all countries are using a comparable method. And what I wanted to know was, how does the calculation methodology influence which activities are reported as resulting in sequestration and which activities result in emission of carbon dioxide? The second thing I wanted to know is how South Africa is currently reporting on carbon in grasslands and whether they serve as a source or a sink. I did a case study by analyzing several documents, both on the calculation methodology itself, which is the IPCC guidelines for national greenhouse gas inventories, and then specific to South Africa, I looked at the reporting. Here, I will narrow the focus to be on sequestration into grassland soils. So starting with the calculation methodology, when counting any emissions or removals, parties make use of the IPCC guidelines for national greenhouse gas inventories. A defining feature of this guidance is the tiering of calculation methodologies into Tier 1, Tier 2, and Tier 3. These tiers are different levels of calculations that range from more simpler in the terms of Tier 1 to more complex and data intensive, such as Tier 3. And the reason for this is so that countries have more flexibility and they can adapt the method to what data they have available. So South Africa uses mostly a Tier 1 method to determine soil carbon stock in grasslands. However, they do use some country-specific information, which would be more like a Tier 2 approach. Now, looking specifically at the calculation used to estimate changes in soil carbon of grasslands. To break this down, soil organic carbon is calculated by multiplying a soil organic carbon reference value by 3 factors. These factors represent different conditions of the grassland. So as I mentioned, we use one country-specific factor when it comes to the soil organic carbon reference value. And this is supposed to be the amount of carbon that's per hectare for this type of land in normal conditions. However, when you are looking at sequestration, you aren't necessarily concerned with the total carbon in the soil, but you want to know how it's changing from year to year. So you want to know about any increases or decreases. And this primarily comes from these 3 stock change factors. And what they refer to is, firstly, there's a factor for a particular land use, then there's a factor for a particular management regime, and a factor for carbon input. And these 3 would multiply together to give you your soil organic carbon value. This is where it gets interesting. So when you are selecting what these factors should be, there's not that much choice. And you have to categorize your grassland into one of these options. So when your first factor, which is land use, you only have one option anyway, so it makes no difference. Then for management, you at least have 4 options. If you think about it, these categories are supposed to encompass the diversity of ways that you can manage a grassland globally. So 4 categories is really not enough to get into really what you can do when you manage a grassland or not do. And then for the last one is the input factor, which is only 2 options. So you can see these are quite crude because you're just multiplying factors together. I've provided some examples of a grassland degrading will result in a 30% decrease of soil carbon over 20 years. And this is regardless of the climate, regardless of the soil type, regardless of what the grassland is used for, if it's used for livestock production or not used at all. This is really just very, very broad categories. And you can already see some of the challenges when you are using these really broad, but also you have a kind of generic, almost universal method to determine what is happening in terms of carbon dynamics that's not really sensitive to what's happening locally. Looking over time at this method, what's interesting is that you can also see that these factors, as well as the categories and the method of multiplying them together, have barely changed in 25 years. You can imagine how much science has developed around understanding carbon dynamics, around understanding grassland biomes. But the only real change we see is, firstly, the addition and removal of a factor, and then secondly, the introduction of factors for specific temperature regimes. Now, this does help a bit when you think about the fact that these factors come from studies, and these studies are done in as diverse grasslands as a pasture that was previously the Amazon rainforest to a grassland in Mongolia. But thinking about how unique grassland dynamics can be, these are still quite broad. So then zooming in on the one management factor called improved grassland, how do you improve a grassland according to this methodology? So there's only one way to sequester carbon above a normal or native condition. And it's very specific in its definition of what an improvement is. And it refers to using any one of these. So there's a specific focus on using one of fertilizer, irrigation, or planting more productive varieties, and then to a lesser extent, using organic amendments, liming, or seeding legumes. Now, it doesn't matter which one you use. If you use any one of these, you can classify your grassland as improved management grassland, regardless of anything else happening there. And if you use 2 of these, then you can add an extra factor of more high input. If you use more than 2 of these together, then that's where the accounting methodology stops recognizing that. So basically, you can see that these factors really make sense for pasture systems. These are usually production inputs, which also need to make economic sense. And another problem with these, although they result in reporting more carbon being sequestered, is that many of these create additional emissions. So if you're using electricity to pump irrigation water, or the electricity used to manufacture, especially nitrogen fertilizer, at the end of the day, it's a question of if you are actually sequestering more carbon than what is actually being emitted to be able to be considered as improving the grassland. And you can also see these are all referred to very specific conditions. For rangelands, where you are using mostly natural vegetation, unless you are changing from what can be categorized as highly degraded or a high grazing density to nominal conditions, that can just get you up to the baseline. So that can be the only thing that can be recognized by this methodology. So then moving on to South Africa's reporting. What's interesting is that South Africa doesn't report on any changes in grassland management. And the reason for this is this requires a lot of data to actually go and collect this. Even though these are very broad categories, you have to know how many hectares fit into each. And you could also argue there's not much benefit to collecting this information because there's much more areas that are rangeland under natural vegetation versus pastures that are irrigated and fertilized. However, what is reported are changes in land types. And the IPCC method allows this to be done relatively easily. And this information is also quite easy to get because you can use satellite imagery. And what South Africa does is they take different satellite photos a few years apart, and then they construct a land change matrix. Although this is deviating a bit from my focus on soils, I was quite surprised by this because this is the largest source of carbon sequestration in the entire inventory, and it also involves grasslands. And this is from the transformation of grasslands into forests. I'm not going to go into the IPCC method for it, but you can imagine it's something similar to how the soil carbon one would work. And basically, when a grassland goes to forest, there's an assumption that it results in more carbon being sequestered. And when a forest turns into a grassland, there's an assumption that there's going to be carbon that's emitted. Now, what's interesting is what counts as a grassland and what counts as a forest. So any landscapes not considered to be cropland or bare ground are divided into these two categories. And this is done based on a threshold. The threshold is if there's more than 10% canopy cover and the canopy height is more than 2.5 meters, it's defined as a forest. You can imagine that based on this, if you have a grassy field with even a few speckboom, this could be defined as a forest. But more generally, a grassland would include pasture, rangelands, also abandoned fields that are now full of grasses, as well as fynbos, succulent, and Nama Karoo. While the forest biome includes indigenous forest and plantations, of course, it also includes thicket and dense bush, as well as the savanna biome. Abandoned fields that are now overgrown with bush or tree woody vegetation would also be classified as a forest. So to give you an idea of the amount of carbon sequestration that's being reported, this value is from the report, and that's the amount of carbon that's being sequestered in the forest land type. Of this value, more than half is just from grasslands being converted into forests. And this is also mostly into open woodland type forests, which means that these are grasslands where woody vegetation has increased to just push it over a 10% canopy cover, but it's still less than 35%. This 54% is a massive amount of carbon. If you compare it to the amount of greenhouse gas emissions South Africa emitted in the same year, it's just less than 10%. While this looks great on paper, included in this figure is the challenge of bush encroachment and alien invasive tree species. Because of the definitions of forest and grassland, it's easy for a few species to get in there and suddenly push it into a forest land type. I'm not trying to imply that any of these problems are being used intentionally as sources of climate mitigation. These documents are very clear about naming these as sources of degradation. However, it's very unfortunate that this calculation methodology really almost only recognizes these activities as being the only ones in which rangelands sequester carbon. At the same time, there's very little management changes that will result in carbon sequestration being reported, which makes it very difficult for this methodology being used as a tool to almost encourage positive management practices that also result in carbon sequestration. So quite an issue that pops up is the fact that very, very different biomes are essentially being collapsed together under this category of grassland or forest. And then based on these categories, assumptions around carbon and how management practices influence them are being made. So grassland systems in South Africa, and by this I'm also including fynbos, snarma, and suckling karoo, are quite unique, especially when you compare it to a pasture system. And IPCC's Tier 1 calculation just doesn't make this distinction, and it represents grasslands globally as very homogeneous and almost a very passive carbon sink. At the same time, locally, these landscapes are extremely heterogeneous. They're also very multifunctional. They have both social and ecological value. Calculation methodologies used in carbon accounting can be highly influential in what is recognized as a source of carbon emissions or carbon sequestration or removal. These influences can be in the form of classifying land, deciding on what is degradation and what is improvement, and simplifying very complex systems into a single unit of carbon, sometimes without using any local science. Now, this is, of course, one method. There are others around which can be better or worse. But currently, it seems that the Tier 1 method will only recognize if grasslands become woodier or if they become pastures. What I've tried to show is that when ecosystems such as grasslands show up in climate policy as sources of climate mitigation, the dynamics around it are really simplified, and there's a gap between what is estimated as this potential versus what is happening on the ground. This society contains a lot of in-depth knowledge on how these systems work. So I would encourage you to critically engage with any carbon sequestration practices, policies, and projects. Really dig into underlying calculation methodologies, data sources, and assumptions, as these can be quite influential. As we all know, these systems are not just single carbon values, but they are really multifunctional, socio-ecological systems. And any practices intended to sequester carbon should be context-specific and align with local knowledge. Good management principles come first, and then only sequestering carbon without creating trade-offs. Unfortunately, I'm not there in person, but here are my contact details. If you would like to get in touch with me, I'm very happy to meet for a virtual coffee or answer any additional questions. Thank you so much for listening. Hi, everyone. I'm Lisa Matthews.
Lisa said she's not online. Is she not online at the back there for questions?
I am online.
Sorry?
Carbon in grasslands.
Yeah, I'm online.
You are? Good.
Yeah.
I think there's going to be a lot of comments and questions on that.
Okay, great.
Yes, and I knew Sue would put up her hand. So yes. There you go.
Phenomenal, thank you. We will be in touch afterwards for various other reasons. Did you look at whether what they're reporting on in UNCCD uses the same calculation or methodology as the IPCC report? Because they also have to report on carbon sequestration with respect to restoration programs.
If I'm correct, the UNCCD is referring to the combating desertification policies, right?
Yeah, that's correct.
Okay. I haven't actually looked at that methodology, but so I wouldn't actually know, but I think that's interesting to look at because they have completely different focus.
Thanks for a really great talk, and alarming as it is, this whole misclassification. But so do you know, I mean, I just can't understand, given that the IPCC is supposed to be working really closely with the IPBS, the biodiversity group, and to avoid trade-offs between climate mitigation and biodiversity. So how is this allowed to continue? Any ideas?
That's a question I also want to know. I'm not sure where the problem lies, if it lies at an international level or if it lies in the methodology, but what I'm seeing is that there's been kind of a lock-in. So you just assume that because you can calculate the carbon value, that it's a scientific thing that you're doing. But this method it hasn't changed in 25 years. It's based on very little information. The original studies going in, I think there's about maybe 4 in the whole continent of Africa. So there's more studies occurring on one research farm in the US than there is for a whole continent. So you have this huge underrepresentation that's going in. At the same time, along with that, you have forests that are the definition for forest, which comes from the Marrakesh Accords, which was a discussion around how to do the first carbon market under Kyoto Protocol. So there's a lot of weird elements coming in. I don't know where the problem lies, or I don't know why things like biodiversity. When I read the writing and I read the text written by the South African government, you can see that woody encroachment is a problem, and that they are mentioning there are multiple goals, including sustainable development. But then when it comes to the numbers and what's being reported, it's a completely different side of it. And I guess what's going to be more important, is it the numbers or is it going to be the intentions? And yeah, I'm not sure how this actually affects on the ground actions.
Just a quick comment. I've tried to challenge that definition of UNCCD, and it is because it's an international thing. And I was basically saying it's impossible, but I think we have to figure out a way, maybe with other countries who are having the same issues, because it does come from an international agreement that apparently took months and months and months to agree on. But yeah, that is the stumbling block.
Yeah, absolutely. And I also think it's also got to do with where the distribution of these ecosystems are worldwide, and also the importance of where are the very biodiversity systems worldwide. It's not in Europe. So I think there's just it's a lot of problems that are kind of just, this is a really big meeting point for a lot of things that are kind of in a lot of different fields of science.
Thanks, Lisa, for that presentation. I'm wondering if you can comment on perhaps maybe do you think there's a lack of consultation with experts on the ground to inform these IPCC, even just the reports? Can you maybe comment on that?
So I think it's difficult because technically South Africa can choose to completely develop its own calculation methodology. That option is available. If you move to the tier 2 and tier 3. The problem with that is then you need to essentially have a national scale survey of exactly what's happening where. And yes, you can work with local consultants, and they do have some data available where you can look at certain changes in carbon over certain areas, but because it isn't occurring at a national scale, it's very difficult to integrate that with and use it as a source of inventory information. So it's also a scale problem. So I think what the government is doing well is when it comes to informing policies around woody encroachment. Well, I don't know, maybe someone else can comment more on this, but it's informed by local science. But when it comes to calculating their emissions and removals, it's not informed by local science. And I don't know, yeah, it's very difficult to integrate just because you have to calculate it on a national scale.
Thank you, Lisa. I think that conversation could probably continue for a while longer, but we don't have the time. But if you want to get hold of Lisa, we can get your email out there. Cool.
Okay, thank you.
Our next speaker is from the Agricultural Research Council in Pretoria, and I apologize if I mispronounce your name. It's Tshedza Matladi. Are they here, person? Okay, or online. Great, welcome. Thank you very much.
Hi, everyone. You can see me, right? This works. Okay, my name is Tshedza Matladi. I am a student at the University of the Free State, and also I'm working with the ARC. Okay, this is part of my MSc. So it's part of an objective that we touched with in my MSc. So my topic is seasonal drought variability associated with El Niño-Southern Oscillation, which I'll refer as ENSO, phases in the South Africa's summer rainfall region. So the summer rainfall region of South Africa will be all the provinces except for the Western Cape, because they receive their rainfall in winter, obviously. So ENSO is one of the major drivers of the interannual climate variability. So just because it's an El Nino here in Bloemfontein, it doesn't mean that we'll necessarily record the same conditions in another province. Yeah, province or town. So there's a slight difference with the regions, then you will see it in my results. So ENSO is made up of 3 phases, which is El Nino, La Nina, and neutral. So mostly in the southern Africa, you would expect to get dry conditions during the El Nino, and dry conditions or drought-related conditions in El Nino, and floods or enhanced rainfall conditions during the La Nina. Then during the neutral year, you would expect to get near normal conditions more. So this study is important because if you take a look at the agricultural drought, you analyze it mostly looking at the 3 months period. So in my objective or in my study, I focus also with the 3 months season. So the aim of the study is to assess the seasonal impact of ENSO phases on short-term drought in South Africa's summer rainfall region, which I might also refer to as SRR. Okay, so I chose 6 stations in the homogeneous rainfall region. So the homogeneous rainfall region map that you see here was adapted from an article by Landman. So this is how he categorized the rainfall regions in his study. So I tried to have almost a station in all the regions that he has in his study. So I have Polokwane, which will fall under the northeast interior. And then we have Mbombela, also known as Nelspruit, which will fall under the low veld region. And we have Potchefstroom, which falls under the central interior. We also have Bloemfontein, which also falls under the central interior. Then we have Richards Bay, that falls under the KZN coast. And we have East London that falls under the Transkei region. So I used reanalysis data from 1979 to 2024. So there are many indicators for ENSO, but in my study, I used ONI, which simply stands for Oceanic Nino Index. So according to ONI, if the sea surface temperatures anomalies are above 0.5 degrees, it will be categorized under El Nino. And if the SST, which is the sea surface temperature, falls at below negative 0.5 degrees, it will be categorized as a La Nina. And if it falls in between, we categorize the year as a neutral year. So I used SPEI, which stands for standardized precipitation evapotranspiration index. So if we got a value that was below negative 0.5, we would categorize it as a dry condition. And if it was between negative 0.5 and plus 0.5, we would put it as a normal condition. And then if it was above 0.5, it will be a wet condition. So I use a contingency table. I would have dry conditions or the conditions of the SPEI on my left, and then on top I would have ENSO conditions. Then from there, I used that to create pie charts. I know the speaker that was here earlier on had something to say about pie charts, but hey, for me it works because it's easier to tell which one gets a bigger slice of the cake. So you'd see with my research, it's it's clear with the pie charts. So for the statistical part, we use the chi-square test for dependence. Okay, so this was what we got from Polokwane. So if you look at, remember I said normally you would expect to get dry conditions during the El Nino, wet conditions during the La Nina. So remember that. So with El Nino, I had 3 seasons that I used. SON simply means September, October, November, which is a spring season. And I had DJF, December, January, February, which was the midsummer. And I have March, April, May, which was my autumn. So all in all, there was no statistical significant relationship when we look at the p-values because they were above 0.05. So when we look at the red represents dry conditions, the white-ish represents near normal conditions, and the blue represent wet conditions. So if you look at the El Nino during the spring season, we had more dry conditions. Compared to near normal conditions, and we didn't record any wet conditions. And during neutral years, we had more dry conditions compared to near normal, and we also didn't have wet conditions. Looking at the La Nina, there was an almost even split between the dry conditions and the near normal conditions and less of the wet conditions. And looking at DJF, this is where mostly you do your planting, I'm not sure, but yeah, if you look at DJF, there was almost an even split between the dry conditions and the wet conditions and more of the near normal conditions. Then with the neutral year and the La Nina, we had more wet conditions and we had more wet conditions between the neutral year and the La Nina. And looking at the autumn, we had, in general, we had more near normal conditions and we recorded wet conditions in the neutral year and La Nina. Okay, so looking at Mbombela, you could see that DJF midsummer had a statistical significant relationship because the p-value was more than 0.05. So we had more dry conditions during the La Nina, which is what would normally expect, and we didn't have dry conditions. And during the neutral year, we also had wet conditions more than the near normal conditions, and there were no dry conditions. And then the DJF El Nino, there was dry conditions that were recorded, which were more than the wet conditions. Then looking at the autumn season, we had dry conditions, but we didn't record any wet conditions. Then overall, during the autumn season, we didn't have dry conditions. And then again, during the midsummer, there was a statistical significant relationship. And then if we look at autumn, again, we didn't have any dry conditions, but again, during DJF, we had more dry conditions during El Nino, which is what we would expect. And then we had more wet conditions during the La Nina, which is also what we would expect. Okay, and then looking at Richards Bay, again, we didn't have any dry conditions during autumn. And if you look at the La Nina part in most of the stations, you would see that there was little to no dry conditions that were recorded depending on the stations. Looking at the East London, we had no dry conditions again during the La Nina. We had more near normal conditions and we recorded wet conditions and we don't have dry conditions. Okay, I'm moving too fast because of time. So if I go through each pie chart, I think I'll run out of time. But okay, in general, what we saw is that dry conditions dominated looking at the inland stations in Polokwane, Potchefstroom, and Bloemfontein during the spring season. And Bombela, Potchefstroom, Bloemfontein had a significant high chance of having droughts during the midsummer. And there were little to no chances, as you saw, during the autumn season of having dry condition, especially in the La Nina. Overall, near normal conditions, as you saw, were recorded, and near normal conditions dominated during the La Nina, yeah. And then in coastal stations, Richards Bay and East London, we had an even split more or less during the El Nino and the neutral years. Then no dry conditions were recorded in the spring season. There are low chances of getting dry conditions during the autumn season, just like in the inland station, especially during the La Nina. Again, here the near normal conditions dominated. Wet conditions were more than dry conditions during the La Nina. Okay, so in conclusion, ENSO faces strongly influenced short-term drought conditions in the summer rainfall region of South Africa, particularly across inland during midsummer. And we can use this information for planning, agricultural planning and water planning, and also for early warning systems in the future. Thank you.
Are there any questions from the floor? Questions? I had a question. So you had your 6 study sites, sorry. And do you think they were sort of sufficiently captured South Africa's climatic and agroecological diversity? And how did you select those sites?
Okay, this, as I said, this was part of my MSc. So with the other objective, it was to compare station data and reanalysis data. So I had to choose stations that had long-term data. So that's how I selected my stations. Yes, yes, yes.
Thank you very much. Our next speaker is Stephan Steyn from the Department of Soil, Crop and Climate Sciences, UFS. Welcome.
Good afternoon, everybody. Right, so I'm going to talk about the development of a Reanalysis-based data, climate database for South Africa, and talk a little bit about the validation of that data. And so the same stations, kind of just a few more than what Tshedza just described, was used here for validation. I'll explain in a moment. Okay, so the background, the problem is, how many of you here has ever used climate data, or wanted to use climate data, and very soon gave up? Okay, 1, 2, 3. Okay, so the problem is, as soon as you need more than a year or 1 season, and you start to look at climate dynamics, and you want 30 years of data at least, and those kind of things, then you are very quickly hampered by big gaps in data. No. And especially more so when you want to look more than just temperature or rainfall or any one single variable. The moment you start to look at combinations of variables like evapotranspiration, which uses temperature and humidity and wind and radiation and all those things, then any gap in one of those is creating problems. No. And so yes, there's methodology like gap filling, but at the end of the day, you don't really know how good the gap filling is unless you have something to compare it to, okay, if there's another station nearby. And so we like having weather service and ARC that collects data and SASRI and all these places, but it's difficult to get your hands on all of it. And even then things happen. No? Stations break, communication errors or whatever, data network issues, whatever the case is, or stations relocate, and therein lies problems. Okay, so reanalysis data then takes all this station data that is available out there and combined with satellite remote sensing and other sources of observations, and along with a model guess field, numerical weather prediction model guess field, it creates high resolution gridded data. But at the back of your head, you always wonder how good is all this reanalysis data. Okay, so the objective was to develop from the reanalysis database point gridded climate data that we can use in climate analysis. Because at the end of the day, it's nice to have a PhD, but you don't want to have a PhD to work with climate data. No, you just want to use it for another means. Okay. So the climate database development, so a lot of programming went into it, but what is available for Ag Era 5 from the Copernicus Climate Data Store is all these variables at the top. So you get your maximum and minimum temperature, your vapor pressure, solar radiation, precipitation, wind speed at 10 meters, I think. And then, yeah, that's it. And relative humidity at specific hours. And so those are available at more or less 9 or 10 kilometers. So it's fairly high resolution, okay, globally. And the nice thing is it's updated monthly. So that is a nice source of high resolution data. But the things are, it's in net-CDF files, and it's difficult for people that's not in that field to work with this kind of data. Yeah. And so when you download the data, it's like aerial. So you choose an area, and it gives you one variable. Okay, so for you to get all these variables at a specific point, you have to download all those files and extract it for a point. And that is computationally hectic. No. And so what I did is chose an area there that covers us and our closer neighbors. Okay, and also then calculate for that area evapotranspiration and logarithmically the wind speed down to 2 meters, and also estimate a maximum humidity, even though it's not perfect, but for that bigger area. And so also link it for each grid point, because funny enough, Copernicus doesn't give you an altitude, so I used a digital elevation model to estimate the height of each grid point. And then with the help of the high performance computing cluster at the University of the Free State, extracted all these files, and long story short, create a grid point climate data set for each point that's easy to download. I can email it to you, and you've got 45 years of data daily, and all those variables are in there, and there's no gaps in it. Okay, but how good is it? Okay, so if you ask me for a data set, I have created an interface where I either put in your coordinates or I click on a map. And if you're happy with the coordinates, it extracts it. It tells me which file to choose out of those. How many did I say? 22,795 points. Okay. So out of those almost 30,000 points, I can choose the correct one. And you can see for this data set, for that point that we chose there in Central South Africa, you have data ranging from the 1st of January, 1979, up to the end of last year. Okay, in the meantime, I've updated it to now, to June. Okay, so that is 16,802 days of variables and all those variables that I mentioned. Okay, so just a little bit about the validation. How does the data look like? So the moment, as I said, you start to ask for data. If you want one variable, there's a lot to choose of. But the moment you start looking at all those variables, so temperature and rainfall and wind and solar, especially if you bring in the solar and the wind, things dive down dramatically where you can get 30 years of data. In fact, not even all of these stations have 30 years of data that I could get my hands on. Okay. And so that's why we decided on some specific stations. No, it's not a perfect spread that's representative of the whole of South Africa, but that's what I have. Okay. So the idea is then to compare for each point, for each variable, how does it look if you take the station data, compare it to the reanalysis data. So in all these figures, there's all my stations. Every time the x-axis, if it's not that clear at the back, is the station data. And the vertical axis is then what I get from the reanalysis. Okay, and the variable is there on the left. So simple scatter plots. So you can see when it comes to something like daily, I also did aggregations to look at monthly means when it comes to temperature, for example, or totals when it comes to precipitation, to see how that compared. So if you look at the maximum temperatures, you can see across all the stations, it was fairly good. Okay, so I have R squareds ranging from 0.7 to 0.92, thereabouts. Okay, so it's good correspondence. What you can also pick up a little bit here is that high maximum temperatures are predicted or not predicted, represented by the reanalysis data. So those hot extremes, it struggles to get those a little bit more. Okay. And so same at the max, if you do monthly aggregations, the values still look quite good. It does drop down in some places. Oh, I should also mention that I eliminated all gaps. So if there's a daily gap or something like that, I took it out. I didn't fill gaps because I'm comparing one thing to another. And when it comes to the monthly things, I used the 60% criteria. So if a month had less than 60% data missing, I threw it out of the comparison. There was also some quality control in the background, so fixing obvious things, but the quality control didn't get everything. If a sensor was, for example, stuck for a few days, it would have made it into the stats here and bring down the verification matrix. Anyway, so minimum temperature, also good. Doesn't look too bad. My R squareds, anything from the lowest here was for Richards Bay, 0.77, and the highest was 0.93 for those two guys there at the top for Potch and Bloem, so the interior stations. What you can also see here again is that the low minimums are again overrepresented by the reanalysis. So just like the reanalysis struggled to get that high maximum temperatures, it's also struggling a little bit to get the very low minimum temperatures going. Okay. Monthly still looks good. Okay. So when it comes to wind speed, I think this is the worst variable to get from reanalysis data. So it depends now what you want to do with the data, no? But in this case, I almost feel like the reanalysis data tells you the wind is always blowing at 1 meters per second, kind of. That's, you know, and so you always get that it's daily. Some places are 0.64 over the interior, but coastal, like there at PE, drops down to 1.9. Okay. So very bad there. Not doing well in terms of wind. Not even if you aggregate it to monthly means. Okay, so still you can see for these coastal stations, then PE even drops down to a R squared of 0.04. So wind speed is not what you're gonna sell in terms of the reanalysis data. Okay, solar radiation didn't do too bad, funny enough. So you can see values are here in terms of around the 0.66670 thereabouts. Okay, so it does get it quite right, but you see also some of the station effects popping up at some of these stations where you see these vertical lines, and so that tells me that the stuck at zero a station, probably for a few days, there was probably an issue with the sensor. Okay. And not so much that it's the reanalysis data that's bad, because the reanalysis data gives you a variation. Well, obviously a lot of station data there in Bloem was stuck close to 0 or something like that. Okay. And living in bloom, it should not really be that often that close to 0. I think we can move on from there. Precipitation. So everybody wants rainfall data. But yeah. Now the thing is, it depends where you are in the world, but in our neck of the woods, mostly we are looking at convective rainfall. And we all know the nature of a convective thunderstorm. It moves over one farm and it misses the one next door. And so in terms of a rainfall station, it's already going to be difficult to get the rainfall right with that. And so remember, in the reanalysis data, it incorporates satellite imagery and things like that. So it gives you perhaps a bit better spatial pattern of where the rainfall was, but at a specific point, it probably averages it out a little bit. So again, you're going to struggle with the extremes, the high values popping through. Okay. So the R-squareds, when you look at daily values, is never good. And that's even if you look at rainfall predictions, really. At the station scale, it's never going to go above 0.3 in terms of R-squared. Okay. But the value of the reanalysis data comes back in when you start to aggregate things to monthly or annual values. So if I look at the monthly values, then you see at least that Mbombela has a 0.73, Potts a 0.64, Bloem a 0.73. So the interior stations looks a little bit better. Even the coastal ones, 0.58, 0.54, and 0.6 for Richards Bay. Okay, so again, one must always ask, is the station data always right? I have to believe it is. Anyhow, that's what's going into the reanalysis data set anyhow. Okay. And then as an example of a derived variable, I see in the last month, the Ag Era has now added ETO as a downloadable variable, but a month ago it was not there. So in this presentation, the ETO values that I'm presenting here is what I calculated using Penman-Monteith. So it uses temperature, max and min, and wind speed at 2 meters, and the solar radiation. And the only thing that I did different is, but there is an alternative calculation of the ETO, is I used the vapor pressure, which is directly downloadable from the reanalysis data. And so you can see, funny enough, even at the daily scale, it doesn't do that bad. So I have values here for 0.51 for Polokwane, 7.1 for Mbombela, 6.3, 6.5 for Bloem. And so everything, the lowest one was East London with 0.45. And you can see there is something funny happening there. And it's probably with erroneous station data that affected it, where the sensors were stuck, like the humidity sensors were stuck on a certain value. If you go back to the humidity data, you will see that that is where the problem originated from. Okay. And so also you'll see that it will overestimate lots of the time, especially if you go to the monthly values for the ETO. You can see that the cloud is mostly on or above this one-to-one line. And so that tells us it's a little bit overestimating evapotranspiration, the reanalysis data compared to the station data. Okay. So my maths is struggling. How much time do I have? So I can also plot out something like that. That's for people that don't like figures, that like values, but that's not me. On request, I'll send you that. Okay. That was point scale. So the question may then be, but spatially, how does it look like? So we can do a very quick spatial comparison. Let's take one case study of a easterly low or a tropical low that sat there over Botswana on a particular date, the 9th of January in 2013. And so looking at trim rainfall values, you can see the rainfall. There was very high rainfalls here in our northern provinces and in Botswana. Okay. And so just quickly looking at the spatial patterns for that day, so you just get an idea of the reanalysis data. So mean temperature, just to combined maximum. So you can see lower temperatures over that cloudy area. You can see the hotter conditions here over Gordonia and the Kalahari. And vapor pressure shows you the higher humidity conditions over that area where the storm was and the eastern coastal regions. The wind speed, not so much to make of that for now, but solar radiation, you can see, was very low. Here it was cloudy and in that cloud-covered area of the storm, and high here over the western dry interior. And the precipitation did pick up the higher values over Botswana and our northern provinces, and even here along the east coast. So if you look at the precipitation pattern and go back to the satellite image, then you can see this. It's not doing too bad. Remember, this satellite image now for one specific hour. The precipitation was for the whole day. No. And then the ETO was then also high here where there was no cloud, lots of incoming solar radiation going up to 11 millimeters for that day, and very low where you had that high cloud cover and rainfall areas. So in conclusion, I think, yes, we can use the reanalysis data to facilitate a lot of climate analysis, but you must use a little bit of finesse in terms of what you use it for. If you are interested in extreme maximum temperatures, then it's not going to be the best thing. You must use it with caution. Or low minimum temperatures, you're also going to set you up to fail. Okay, wind. Don't plan a wind farm around reanalysis data, perhaps. No. Okay, so the things that did do well or didn't do well was wind speed and obviously daily precipitation, but monthly did better. The temperatures was good, solar radiation was good, and even a derived unit like evapotranspiration did astonishingly good. Okay, so it is a possible alternative for climate analysis. Right, thanks. That's it from me.
Do you have questions from the floor? Okay.
Thank you, Stephan. This is a very selfish question, but I have an unpublished manuscript using a lot of climate data, and I would love it if you wouldn't mind reading it to see where my goals are.
I have a lot of unpublished manuscripts. Pleasure.
I've also got a selfish question.
Of course, that's why I'm here, because you guys use the climate data. So it's like we can combine and work on things, but you know what you want out of it.
Do we only access this data by emailing you and getting it as an attachment, or is there some other way to access?
The idea is that we actually developed it as part of a WRC project for, I don't know whether you're familiar with SAPWAT. So it's like an irrigation tool that people use around the country. And so I think even the pasture people, it's set up for maize and what. But the problem with SAPWAT is firstly Windows 11 issues that suddenly crept in, and so now it's not always working. And the database that it was historically using, very good database, was this one developed by UKZN, but only went up, that quaternary catchment database that went up to 1950 to 1999. And so that was never updated. And perhaps 10 years ago, it was 10 years old, but now it's 25 years old, and it's a problem, especially in the light of climate change. And so the idea is to develop, to have that as a built-in thing in there, but it's not there yet. We're not finished with that project yet. But in the meantime, you can email me. Thanks.